So here we're going to look at a projection at an angle to the horizontal rather than something just being horizontally projected. It's just being thrown up and out. So it's projected at an angle of theta to the horizontal. And we're going to see this kind of flight path here. It's going to be symmetrical. It goes up and then it comes down, and that's a symmetrical flight. But what we're going to do is we're going to consider almost exactly the same as before. We're going to consider the horizontal effect of this flight and the vertical motion in this flight as well. But one thing we need to be careful about is that when we're looking at the velocity, the initial velocity is at an angle theta to the horizontal. So when we consider horizontal motion, we need to resolve that horizontally. And when we consider the vertical motion, we need to resolve the velocity vertically. So horizontally, we're going to look at u cos theta. We're going through the angle of theta, so it's u cos theta. And that's not going to change during the motion, during the whole journey. Okay, the horizontal velocity will stay the same, just like in a horizontal projection. When we look at the vertical velocity, the initial vertical velocity is going to be u away from theta, so u sine theta. And that will change, that will get slower due to gravity, and then it'll eventually stop, and then it'll start coming down again. As I said already, the path is symmetrical. And one thing we do know that at its greatest height here, the velocity will be zero, the vertical velocity, sorry, will be zero, because it'll have stopped going up and it'll just be about to start coming down. So it'll go from a positive to a negative velocity, or a negative to a positive velocity, depending on what you're treating as up. So let's have a wee look at an example here. Particles projected from a point O with a speed of 30 meters per second, here we go, at an angle of A, alpha, above the horizontal, where sine A is equal to 3/5. This is quite a common way of writing things when you have a nice angle that can be done as a triangle like this, where sine is opposite over hypotenuse is 3/5. So you can make up a little right angle triangle there, where the opposite is 3 and the hypotenuse is 5. Now, because it's a right angle triangle, Pythagoras' theorem tells you that that's a 3, 4, 5 triangle, which means if I know that sine alpha is 3/5, cosine alpha is 4/5, adjacent over hypotenuse 4/5. And we could work out tan alpha as well, opposite over adjacent 3/4. But we're only going to use these two values. And just means we don't have to actually work out the angle. We can use quite nice numbers like 3/5 and 4/5. So let's look at this vertically and horizontally, because we're asked to find the greatest height reached by the particle. And at the greatest height, we know that the vertical velocity, vertically the velocity will be 0. Now vertically, its initial velocity was 30 sine alpha, or sine A, I've got it in here. And I know that sine alpha is 3/5. So 30 times 3/5 is 18. So its initial vertical velocity is 18 up. The height, we want to know that. And I guess we should have the acceleration here then is minus 9.8. Okay, if I'm treating up as being positive, then gravity is going to be minus 9.8. Not minus 10 or minus 9.81, but in maths we use minus 9.8. So using our UVAT's equations, v squared equals u squared plus 2as, we can fill that in and find out what h is, and it's 16.53 meters. So that's the greatest height that it reaches. Now the particle strikes the horizontal through O at Q. Find the distance OQ. So let's see where we go then from here. So we've got our horizontal. It goes up and then comes down again. So this is Q and this is O. And again, we know our vertically. This is U sine alpha, which we've already worked out is 18. Because I'm treating up as being positive, acceleration is due to gravity, it's minus 9.8. And the displacement is 0, because when we're talking about coming back to where we started in horizontally, its displacement is 0. What is the time? And so when we fill those all in, again, we find that the time is either 0 or 3.673. And that's what we'd expect. A time 0, it's at O, and at 3.67 seconds, it's at Q. Now, it didn't actually ask us to find the time, it asked us to find this distance, OQ. But we know that when we look horizontally, distance is speed times time. Now, the speed, well, if u sine theta is the vertical velocity, u cos alpha, sorry, not theta, is the horizontal speed initially. And we've worked out already that cosine alpha is 4/5. So that's 30 times 4/5 times the time, which we've just worked out. And that works out then as 88.2 meters. Second example. This time a ball is projected from O at the top of a cliff with speed v meters per second at an angle of 30 degrees. So this time we don't know the speed, but we do know the angle. The greatest height reached above the horizontal is 4.9 meters. Show that v is 19.6. And given that O is 60 meters above the sea, find the time taken for the ball to reach the sea's surface. Okay, so first thing first, we're told that the greatest height is 4.9 meters. So we know that vertically, whenever we're talking about greatest height, then the speed, final speed, must be 0. Its initial speed is v sine 30. We're going away from 30, so it's v sine 30. And sine of 30 is a half, so its initial speed is a half v. Now, if I'm treating up as being positive, then my acceleration due to gravity is minus 9.8. And we know that it goes up, it has a maximum height of 4.9. So again, filling all those answers in, we get the v squared is 3 at 4.16, and so v is, as we wanted, 19.6 meters. Now, secondly, we're asked that, given that O is 60 meters above the sea, find the time taken for the ball to travel from here down to here. Okay, so it's all this distance. Now, to this point, this is symmetrical. So I know that if I find half what the time to that the greatest height is, then if I double that, I'd get the time to that point there. But actually, after this, it becomes not symmetrical because we've got this next wee bit to go down below O, or below the horizontal. So what we're going to do vertically to sea level, I'm still treating up as being positive. So if it goes down by 60 meters, my displacement is minus 60. My value of A is minus 9.8. Its initial speed vertically is u sine 30. And we worked out, v sine 30. We worked out that v was 19.6 and the sine of 30 is a half. So its initial speed vertically is 9.8. And we want to find what t is. So again, we put that into one of our UVATS equations. This time we get a quadratic equation, which we just use the formula for, and we get two answers. One is 4.639, or t is minus 2.639. Now, imagine if you sort of go back in time, it's going to be minus, so you get that symmetric shape there. But that's not possible. We can't go back in time. And so our final answer here is 4.639. And that's how we project something at an angle to the horizontal. We still go about looking at things vertically and looking at things horizontally, but we just need to make sure that the velocity is resolved either horizontally or vertically, depending which component we're looking at.